So it's actually pretty straightforward to see that double Q learning is indeed unbiased, unlike regular Q learning, right? Which is at least initially biased. Of course, that the noise will be reduced over time, but Q learning can suffer significantly initially. In the initial stages of training, we see a significant bias, and then over time it is mitigated. But in any case, it's easy to see that double DQN does not suffer from this maximization bias because the returned value from Q1 is independent of the maximizing action from Q2. And the pseudocode for double Q learning is actually a very simple extension over the Q learning algorithm that the off-policy TD Q learning algorithm that we just saw a second ago. For double Q learning, we simply, as I said before, we initialize two different Q networks, and at each step we update one but not the other. Right? And each time we update one of them, we use the other network to compute the argmax value, right? And as long as we keep these two networks, these two Q estimations, not necessarily network, right? Currently, actually, we only consider them as tables. Later on, we'll see them as a network. But let's call them just Q approximations. So as long as we update these two Q approximations independently, we are guaranteed to be unbiased. We are guaranteed to resolve the maximization bias issue. So let's see some results. So indeed, for the example problem that we've seen earlier, right, to demonstrate the issue with the maximization bias, we're gonna see how double DQN, how double Q learning impacts learning in this domain. So you can see that indeed Q learning suffers from significant initial bias in this domain. So just by the way, the x-axis here is the training episode, while the y-axis is the percentage of left action from A, which is the optimal action, right? We'd like to learn that we should... Sorry?
Suboptimal action. You want
to sorry, right. That's the suboptimal action. We want to reduce this, the amount of time that we're taking action A over time, right? We never get to 0 because we have some epsilon greedy approximation that is set to 5%, but we would like to reach that epsilon as soon as possible, meaning that we learned that the optimal action to take based on the Q values is the other action, is the right action. Indeed, you can see that Q learning suffers from significant initial maximization bias, right? Initially, it thinks that going left is beneficial, is better. Why? Because it has some samples from going left that seemed very promising. We know that this is just a fluke, right? Shouldn't expect that. But for regular Q learning, doesn't know that, and it suffers from this maximization bias. So initially, you can see that it almost reaches 100% certainty, or 100% time of the times that it actually takes action left. While double Q learning does not suffer from this issue at all. From the beginning, we see that it is able to understand that going left is probably not a good action to take.